There we go. Alrighty, so today we're going to officially start Chapter 5 material because what we worked on the last 2 days was Algebra 1 material. Getting you ready for the Chapter 5 material. So Chapter 5 actually begins with reducing radicals. And we have reduced radicals this year before. We already have. We do it with numbers. Remember when I asked you to memorize some perfect squares, some perfect third powers, and things like that? You guys remember all that stuff when we were reducing just the number radicals? Okay, well we're going to be doing that some more, only now there's more than just numbers. There's letters too. The really good news is, honestly, doing radicals with letters is easier than radicals with numbers. But I do want to start by reminding you of the things that I've asked you to memorize. Remember, as long as you do all your homework and you can stay off your phones during class, you have open note tests, which includes what I'm about to write, the powers that I've asked you to memorize. So as long as you're doing your job, you don't even have to memorize them. Let's start with the third powers, because I don't have enough space to write all the second powers, and I'm hoping you've mastered all those. Fingers crossed, fingers crossed. So we'll just start with the cubes. 1 to the third doesn't matter, so start with 2 to the third. I asked you to know that 2 to the third was 8, and 3 to the third is 27. 4 to the third, getting big now, 64. 5 cubed is 125. And I told you you don't need to know bigger than 5 to the third power. I mean, if you care, 6 to the third is 216, I think. It's even how I said I think. Yes, it's 216. 7 to the third is 343. 8 to the third is a big number. 8 to the third is 512, or is it 256? 4, 3, 12. Oh no, 8 to the third is even bigger than that. 8 to the third is 4096, and I don't know anything after that. So I think it's 4096. They're big, they're big, they're big. So this is as high as you need to go on the third powers. I need you to know a couple fourth powers, which I've already talked to you about. I would like for you to know that 2 to the fourth is 16. And I would like for you to know that 3 to the fourth is 81. I don't need you to know any more than that, because they start getting really big. I mean, 4 to the fourth is 256. 5 to the fourth is 625. I mean, you see how fast these things get really, really big? So that's good on the fourths. And I do want you to know a single fifth power. I would like for you to know that 2 to the fifth is 32. Cool. We are ready to rock and roll. Alrighty, so the first example is a cube root. We've done cube roots of numbers before, so hopefully everybody in the room could handle the cube root of 27. But we've never seen it done with variables. So I'm going to do this question in a way that just demonstrates a rule. Not that I expect you to ever do it this way after this one time. Okay? I'm only doing it this way to show you that a rule is true, rather than me just tell you, hey, this thing is true, trust me. I don't like doing that. So I would rather just show you it's true and then be like, okay, so by the way, from now on, just assume it's true and use this trick. Okay? Okay. What do square roots cancel? Do we know? Squares. Yeah, so what do third roots cancel? Cubes. I mean, their job is to cancel third powers. Just like a fourth root's job is to cancel a fourth power, and a fifth root's job is to cancel a fifth power, so on and so forth. So we want this radical, this third root, to be able to do its job. Fine. Hopefully, we recognize 27 as a perfect cube, especially since I just wrote it. So I know it's going to be able to do its job on that 27. So just let me write that 27. Now, I'm not used to exponents inside my radicals, but I do know that a third root wants to cancel a third power. And in the last 2 days, we reviewed the fact that when you multiply two numbers with the same base, you add those exponents. That means I should be able to split this x up into several x's that are third powers. Specifically, because when you multiply numbers with the same base, you add their exponents, so 3 plus 3 plus 3 is this 9. I would never expect you to do this much work for these. I'm just demonstrating why what I'm about to show you is true. And the same thing with this y to the 6th, eq. Not quite sure what to do with the 6th, but I do know that third roots cancel third powers. The 27 is already a perfect cube, so I don't need to do anything with it right now. I could, but you already know what the third root of 27 is. Don't worry about it. You'll see. You'll see, okay? I'm going to write this as y to the third, y to the third. Now, this radical is full of things that the third root can do its job on. It can do its job on every one of those 6 things that I've written. And just like we learned before, when stuff comes out of the radical, you just multiply it to each other. I mean, it was multiplied on the inside, right? So when it comes out, it's still multiplied. So we bring this stuff out. The third root of 27 comes out as a 3, which is what I believe you were asking me, Mason. So we're doing it now. Third roots cancel third powers. So right here, that exponent has been canceled. Right here, that exponent has been canceled. And right here, that exponent has been canceled. This one gets canceled. Third powers canceling third roots, and third roots canceling third powers, vice versa. And same thing with that one. And well, since the radical was able to do its job on all of these pieces, there is no more radical. But no one writes 3x, y. No, what you would write is 3x to the third y squared.
Wait.
Yeah.
So does that mean that pretty much when you divide like a root into that you just divide it?
So what Gavin just realized is what the shortcut is.
Yeah, that's wrong.
Radicals divide exponents. And you notice over the last few days when we were discussing all those rules, I never spoke about division of exponents.
So this is the division? Okay.
Yeah. Yep, but that's too much work. See, I could have just told you, hey, radicals divide exponents, but you're just right. But now you directly see it. Oh yeah, 9 divided by 3 is 3. 6 divided by 3 is 2. Mr. M, 27 divided by 3 is not 3. I'm aware. That's because 27 is not a letter with an exponent. A 27 is a number. We reduce numbers the same way we always did. But when you have exponents, you divide. Yeah, I just said what is the third root of 27 because we know that 27 is a perfect third power. So we said what to the third power to give me 27? Yeah. Well, hold on. Right. So, but that's the trick, guys. Never do this. This is just why it's true. When you have to root something with an exponent, you divide the exponent by this root type. And there is academic vocabulary for that root type that I'm going to be using from now on. That is called the root index. So you divide the exponent by the root index. This index is a 3, this index is a 3, this index is a 4, this index is a 5, so on and so forth. So from now on, I'm not going to be splitting them like that. That was just me showing you why the rule works. Is that a question or just a stretch?
I do have a question, but those are start to answer.
Okay.
I was wondering what's going to happen
If it doesn't divide? Yeah,
Yeah.
you shall see. It's coming up, I promise. But it's good to wonder about it. Let's tackle this one. Now we've got a list of third powers at the top of the page. 128 is not one of them. That means we need to figure out which of those third powers does go into 128. And one of them does go. 64. Yeah. Michael W was gonna say it too. I saw it on his face. But yeah. We can bring back eyes, and we will probably in the homework, but not today. No, because it's division. Because you can't divide 128 by 125. Because what we split these into strings of multiplications. We need to take the 128 and split it into multiplications.
Okay, I was just thinking what.
Mm-hmm. Yeah. So we call it 64 times 2. And I'm going to go ahead and identify the 2 as something that radical can't do its job on, so that number's stuck. So I will be circling the stuck things. That way I always know, yeah, those objects are going to be inside a radical still. And can I divide this exponent by this index?
Yes.
Cool. Since I can divide it, I don't need to split it. Oh, cat's out of the bag. When you can't divide it, you have to split it into things that do work, just like we're doing with the numbers. And the remainder will stay in, yeah. So, here we go. The cube root of 64 gets to come out. The cube root of 64 is 4. Hop over this. It's stuck. When the x comes out, what will its new power be? It'll be a square now. Yeah, 2, because 6 divided by 3 is 2, so it comes out. And we do still have a radical here. Cube root of 2 is stuck. Can't do anything with it. Boom, there you go, finished. Oh yes, you definitely have to. The root type didn't change. It is still a cube root. What's that?
I mean, I said it makes sense.
Yeah. What did he say?
He said that's back.
Okay. You mean will the index change? Going forward, I will be showing you how to do that, but not today. Okay? All right, ready? Let's check out the next question. This is a fourth root. Its index is a 4. Is 16 one of my perfect fourth powers? Jason's thumb poked up above the black barrier. So yes, 16 is one of my perfect fourth powers. That means I don't need to split the 16. I'll just leave it as a 16. However, I cannot divide this 9 by this 4. So just like we had to do with numbers that we couldn't root, we have to split the x. So there will be 2 instances of an x. One of them will be the exponent I could have divided by 4, which would have been 8. And the other one is the remainder. If there's 8 of them here, then there's 1 left over. And that object we know will be stuck. That was the whole purpose of splitting it. Can I divide this exponent by the index? Yes, I can. Then there is absolutely no reason to split it. Things that are not circled get to escape this radical prison. Yes, you need to split it, and what you're trying to do is you're trying to split it into the biggest thing you could have divided by the index, and then technically this is the remainder. Imagine you did 9 divided by 4. But the remainder would have been 1, right? Not probably. It would have been a remainder of 1. So the remainder is the leftover exponent, which is what Mason mentioned a minute ago. That's what he was talking about. Alrighty, so things that are not circled get to escape. Fourth root of 16 is 2. Remember, we don't divide the numbers, we reduce the numbers. When the x comes out, what will its new exponent be? 2. Remember, it's division. It's division. It's 8 divided by 4. And the same thing on the y. 8 divided by 4 is 2. By the way, having it out here with a fourth power is one of the wrong answer choices that would have been on my test. Because students forget and they just subtract. But this is division. And Mason, hold on. I'll clear up your brain in just a second, okay? And then there's a fourth root of x still here. I'm not going to write to the first power. Now, Mason, a minute ago you told me the remainder stays inside, right? But I'm going to ask you a very simple question. Don't stop looking at the letters. What is 9 divided by 2? And don't be afraid to say with remainder. 9 divided by 2 is... Excuse me, I said the wrong number. What is 9 divided by 4? No. I said no decimal. I want him to say with remainder.
Oh.
So 9 divided by 4 is 2 remainder. 9 divided by 4 is 2 remainder 1. Okay? What's that? Look, right here. It doesn't get to come out until the division has occurred. So this 9 divided by this 4 gives me this 2 and this remaining 1.
When you split it up to x8, x to the power of 8.
Well, hold on one second. Let me finish with Mason still asking, and then I'll get to you, Matthew M. So Mason. Okay, so right here, let's look all the way back up to the top because he's confused how I got the 2. Right here, this 9 divided by this 3 is this 3, right? This 6 divided by 3 is this 2. This is not a square root, it's a fourth root. So this 8 divided by 4 is 2. It's not a square root, it's a fourth root. And now Matthew M, you were asking me about this thing? Well, this is the part of the radical that just didn't reduce. So it's still part. Yeah, there's nothing to do with it. And there wouldn't be this little 1 in here. I just did that to show him that it was still 2 remainder 1. But yeah, yeah, whatever doesn't come out is stuck. I mean, you can't do anything with it. There it is. It's got to still be in there. It's part. Yeah. So again, I think that doing this stuff with letters and exponents is easier than doing it with numbers. Because to do it with numbers, you have to know how to multiply some big things sometimes. But when you're doing it with exponents, the numbers are much smaller. That's good news for us. A fifth power. Eek! Well, I already told you the 1/5 power I want you to memorize. 2 to the 5th power. It's 32. 4 is much smaller than that. That means there is no 5th power hiding inside of the 4. 1 to the 5th doesn't count. That 4 will be forever stuck. Now the 8s. I mean the A's. Its exponent is 8. Clearly can't divide it by 5 pretty. So since it doesn't divide pretty, I need to split it into an exponent I can divide by 5 and what would be left over. And yeah, it's just 5. And yep, and you would get 3 as the leftovers. Absolutely. When it comes out, it will. And it'll be stuck inside, yeah. Yeah, so, well, hold on, don't steal all the glory now. Now, on the B's, I got to do the same thing with the B's. I have to split them. What would be the exponent that I can divide by 5? Lots of people would be great. 10. You can divide 10 by 5. And, well, if 10 of them are here, you still have 4 more. And, okay, I can divide 5 by 5. So I don't need to split the C's at all. Let me go through and identify the things that are stuck behind. I know that that guy's stuck. Oh, we know the 4 is stuck. Forgot to circle it. And we know that one is stuck. So 3 objects will get to come out. 3 objects will have to stay in. That's just the way it works.
Wait, what?
Hold on. 2 people ask. Okay, Jason first. What's up? Well, okay, so I split the 14 into 2 numbers. You know when you multiply 2 numbers of the same base, you add their exponents, right? So 10 plus 4 is 14. I needed to know what number smaller than 14 can I divide by 5. And 10 was the first option as you counted down. And then it was like, okay, 10, so I needed 4 more of them. That's how. And then, I'm sorry, Anna, what's up? Oh, okay. Alrighty, well, things that don't have red circles get to come out. When this A comes out, what will its new exponent be? Well, I mean, it has to have an exponent. It'd be a 1. Now, we don't have to write the 1. We don't want to say nothing because a to the 0 equals 1. But we just say it's got nothing to write because 5 divided by 5 is 1. Skip over this guy. It's stuck. When the B comes out, when this B comes out, what is its new exponent? You can say it a little bit louder. 2, 4 squared, yeah. Because 10 divided by 5 is 2. Skip over this when it's stuck, and just like the A, whose power was a 5, C to the 5th, when it comes out, it's going to have that power of 1 that we don't need to write. So 5 divided by 5 is 1. Now you could write it. It's not wrong. It just won't be typed on my test. The 5th root still exists because it had red circles in it, and the 3 things in red circles are going to still be in there. 4, A to the 3rd, B to the 4th, and you're finished. And that's it. Yeah, that's it. That's as far as it simplifies. I think 12. And yes, there are questions exactly like this on the test. Yeah. I don't know, actually.
Is there like direct questions like you?
Not did I take it right off the notes and put it on the test. I changed the numbers.
No, I'm not saying like exactly.
Yeah, no, they're identical, they're like done just like this. Yeah.
Yeah.
Yeah. No, stop. Everybody's panicking. Anything major going to change in regards to what? Is the question. Well, as far as just reducing radicals is concerned, the only way that I could make this any more challenging is fractional exponents, which we're going to get to next week. Because tomorrow we're practicing. We start fraction exponents on Monday. Tomorrow's Friday, yes. Alrighty, right here. You see this negative 3x that's sitting on the front? It's got a multiplication dot right there. So what do we do with it? We look at it. Exactly. So until we simplify this radical, we're just looking at this negative 3x. It's just hanging out, waiting for things to happen to it. Yes, but it's not distribution. So Mason want to know, do we multiply everything by the 3x? Yes, but realize, Mason, it's not distribution because everything that's in there is already being multiplied. So when it comes out, it's just a string of multiplications. It's not a distribution. So the little 4 is just telling you that it's a 4th root. That's all that's telling you. No, it's just telling you it's a 4th root. Its job is just to reduce 4th powers. So 32 is not one of my 4th powers. But 16 is, yeah. It's 16 times 2. I cannot divide this 9 by the 4. So I need to split. Oh, let me circle my 2. It's identifying it as stuck. I got to split the x's. The number that is smaller than 9 that I can divide by 4 is 8. Yeah. So if 8 of them is here, there is still 1 left over. And yeah. Because at the top, we have some of the 4th powers. How far is it? There it is. 16 is one of them. See, the 32 is just a number. It's not an exponent, so it behaves according to the older rules. And we go, okay, what perfect 4th power goes into 32? 16 does. Right. Alright, so we identify this as stuck. And also, I can't divide 7 by 4 pretty, so I will have to split the y's. What number smaller than 7 can I divide by 4? It's 4, and 3 are still going to be stuck in there. Absolutely, go for it. You don't have to push too hard. There we go. So 3 things are going to come out. 3 things will not. And we do have a negative 3x just hanging out there right now. Objects that are not circled. What is the 4th root of 16? It is 2, not 4. Be careful, you're not dividing the numbers, you're reducing the numbers. Now things with exponents, you do divide the exponents. When this x comes out, what is its new power? It is going to be x squared, x to the second. And when the y comes out, its power is 1. Yeah, 1. And so there's no reason to even write it. I'm going to go ahead and write my 4th root of 2x y to the 3rd. And we are finished once we multiply this right here. Because we got x squared because we did this 8 divided by this 4. Remember, it's division. You keep subtracting, don't you?
Like when I split up the 9.
Oh, okay. So when you split the 9, you said 4 and 5. But here's the problem. 5, the 5 is still larger than the index. So if you have a power that is larger than the index, you're not finished. Hmm?
That's what I thought.
Index is the type of root it is. Fourth root, fifth root, square root, third root. So if you have an exponent that is still equal to or bigger than the index, you haven't finished reducing.
Or if you go to 9
Exactly. When that was the thing. But what he did is he split it into 4 and 5 because in his mind I can't divide 5 by 4 and I go, yeah, but 5 can be split into 4 and 1 again. So, and the what now? I took the fourth root of 16. Yeah, that's where that went. Yeah, well, so they come out one at a time, and since they were multiplied on the inside, they will still be multiplied on the outside when they get out. Yeah, this too is right there because I can't do anything with it. That's why I had it circled in red because I knew it was going to be stuck. No, I mean, this is what we did with the 5s, and it's what we did with the 3s. Yeah, I mean, we're just reducing our numbers the same way we always did. Some stuff will get out and some stuff will get stuck. And Bryson, what's up?
for the final answer,
Yeah.
for negative 2x times 2x squared, how did you get the 2x squared?
Well, the 2, and I'm not done yet. I still have one more step to take. But the 2 is because imagine none of this existed, and I just said, hey, what's the fourth root of 16? It's 2.
Yeah.
And then this x squared came from that, like that, okay? So they're one piece at a time, but because they had multiplication dots between them on the inside, when they come out, they have multiplication dots in between them still. And the last thing we need to do is actually multiply this. You can multiply anything you want to in this world. It doesn't even matter. So you multiply the digits, negative 3 and 2. It gives me negative 6. And then you apply some of the rules that we talked about the last couple days. X times x to the second is, come on guys, multiply these two. What are you going to get? You're going to get x to the third.
Wouldn't it be negative 3x to the 3rd?
Negative 3 times 2 is negative 6. There's like a little hair or something stuck in the ink of my pen, and it's making a huge mess. You see that? Yeah, I was just trying to fix my exploding pen. Yeah. No, okay, so we don't multiply. We don't, this isn't distribution. It's just strict multiplication. So you multiply numbers, you multiply x's, and if you had y's, you'd multiply y's, but you don't. Because there's no pluses or minuses.
Just adding the exponent.
Right, we're just adding the exponents because when you multiply two numbers of the same base, you add their exponents.
That would be negative 6x.
Hold on. There was no other y. So the exponent on the y doesn't get affected.
So the one in the root then, or 2x is that?
Oh, but this is just stuck. We just have to write that. I'm just not done yet. There's nothing you could do with this anymore. See, we cleaned that part up first. Once the radical has been cleaned up, it's done. You can't do anything else with it. This looks like total garbage. Oh well. Can't do anything about it now, can I?
So what's the final answer?
That's it. You're looking at it. That's it. You can't do anything. Yeah, everything's been simplified. Everything's been multiplied.
Can you read the final answer?
Negative 6x to the third y times the fourth root of 2x y to the third. Did you check out Zenny Optical yet? You should.
I have a appointment on Friday.
Oh, okay. Right here and right there. Nobody asked, but Mr. M, how do I know that that wasn't an exponent on the x? How do I know that that's not an exponent on the y? The way you could tell is because the little number is directly above the radical. That shows you that it's part of the radical. And you see there's a space there. That is honestly a space that I typed. And it'll look like that on the test to make it obvious that no, that was an index. It was not an exponent. Okay. And if you're not sure come test time or come homework time, you ask me and I'll tell you if that's an index or an exponent. All right. Let's tackle the last question. we have a 4x squared y on the outside, and it's going to stay that way. Can't do anything with that. But the inside, yet, of course. But the inside, we can clean up. So someone asked me at the beginning of the lesson, are we bringing back imaginary numbers? I could. Is this one going to have imaginary numbers? Well, what is negative 2 times negative 2 times negative 2? Negative 8. You see how you said a negative number? So then what is the cube root of negative 8? It's just negative 2. No, not I. Because negative 2 times negative 2 times negative 2, which is, by the way, negative 2 to the third, is negative 8.
You have a negative inside the radical?
You can have a negative inside an odd radical without okay. Let me flip the notes over. Would you just wait a second?
Would it be 27 times negative 2?
No, stop it. Look, negative 2 to the third power is negative 8. So the cube root of negative 8 is strictly negative 2. See, because a third root here would give me back negative 2. Okay. The point is, because it's an odd indexed root, it's just going, and you're taking the odd root of a negative number, you will strictly get a negative result. Because an odd number of negatives is always going to be negative. That's why. Excuse me. But here's the problem. It's 27. What do you mean the 2? There's no 2. Oh, you mean when you split it?
Yeah.
Oh, well, here's the thing. You can't leave a negative sign in the radical in your answer. So when you split this negative 54, no. When you split this negative 54, you need, just like when we were dealing with the imaginaries, you need the negative sign to be strapped onto the thing you're going to reduce. Mason has already identified the number 27 as our perfect third power. So we will split this negative 54 into a negative 27 times a 2. The 2 is stuck. This x to the 9th, do I need to split these x's? No, because I can divide 9 by 3. These y to the 7th doesn't need to be split. Yes, it does, because I cannot divide 7 by 3. So when I split it, what is the exponent that I can? 6 and 1. Identify that guy right there as stuck, and do that. All right. Again, hold on. Again, 4x squared y hanging out there, waiting to be multiplied by whatever comes out. Let me flip the paper over real quick and show you that negative 3 to the third power is negative 3 times negative 3 times negative 3, which is negative 27. That means the cube root of a negative 27 is simply negative 3. Not I. I is only involved when you have to take the square root or the fourth root or the sixth root, basically even roots. I is only involved in even roots. When you have to take the even root of a negative number, you are dealing with an imaginary. You take the odd root of a negative number, it's just negative. Because an odd number of negatives will always give you a negative. And feel free to write whatever you'd like to on your notes because you plan on having an open note test. All right, so the cube root of this negative 27, which I just wrote on the back, is a negative 3. Yes? An odd root of a negative number is negative.
I like this
Mm-hmm. Good. What is the exponent on this when it comes out? Yep, 3 because it's division. And the exponent on this when it comes out? 2. Not 2 because it's division. Yeah, and you don't have to write the 1. Now, if you write it, you're not wrong, but I'm not going to write the 1. And all we need to do now is multiply here. Again, there's no distribution, it's just multiplication. So we do 4 times negative 3, which is negative 12. Let's see if I can use my green pen without it exploding. We are add the add those exponents because you're multiplying numbers at the same base, so x to the 5th. And then this is a purple marker or a purple pen that's hard to tell, it's different from the blue. But yeah, when you multiply those two numbers at the same base, you add their exponents, you get y to the 3rd. And this is just there. Don't lose that radical, it's part of the answer. And that is everything.